Okay. With that, yeah, so basically everyone who's coming today, I think, is here. So let's talk about time series. So this is both a data structure and a causal structure. And so when dealing with time series, we have the challenge of both building a causal model that corresponds to the temporal relationships that we want to describe. But it turns out that also we have to deal with different statistical issues because things like the law of large numbers that we are used to relying on in the cross-sectional setting get kind of iffy. We need some extra conditions for them to hold, and they don't always hold in general, and whether they hold will depend on features of the series that may be things that we're trying to infer. So that's a challenge, and so I'm going to give a very brief tour of inference estimation for time series data, and then an introduction to a small part of time series causal inference with a focus on estimating the effects of what are referred to as shocks or point interventions. So this is the idea of a one-time intervention to a quantity like, say, the level of government spending, the federal funds rate, or some other policy. And then the goal of causal inference for these kinds of interventions is to figure out not just the effect on other variables in the system at the same time, but also how those effects play out over time. And so I'll talk about some estimators that get used for this and what their properties are. Okay. Good. Okay, so what is a time series? It describes data which is ordered in a sequence, things like quarterly macroeconomic aggregates, output and prices, monthly unemployment reports, stock prices every second, every millisecond, or however fast people are trading at nowadays. Maybe faster than per millisecond, I don't really know. And the key to these time series, what makes them distinct, is that the index for the observations that we're going to call OT, so this is going to be some vector of variables. So in the cross-section, the index was effectively arbitrary. We called an observation I, but one observation was as good as any other, so the actual number I didn't matter, just it was a unique identifier. Here the actual number matters because it reflects an ordering which may be reflected in both the statistical and the causal structure. And so the goal of inference with time series is to use the historical behavior of the data. So in general, we have data about the past, and our goal is to learn about the properties of the sequence as a whole, and potentially about future values of the series to the extent that we have a probabilistic model that allows us to say something about that. And so the statistical complications should be handled. So dependent observations means that we are not just interested in the structure across variables within an observation, but we're interested in potentially correlation, statistical dependence across observations. And that will impact estimation and inference. And a lot of challenges that arise from that make discussions of what you're doing in time series estimation and inference a little bit different from the situation you face with cross-sectional data, because ideas like identification, which are defined in terms of, say, the known probability distribution, are often linked to, though not necessarily identical to, this idea that you might, given enough samples from this observation, from this distribution, learn the distribution. And so knowing the distribution is something that is at least potentially feasible or approximately feasible. For time series, this may or may not be true. So more observations may be giving you observations of just something different. And so you're not learning the distribution that you're necessarily interested in. And so there are cases in which you do learn something about the distribution. And so identification in the sense of relating the distribution of the causal quantities, the quantities defined in terms of structural model, to the distribution of the observed quantities is still something that you can work with, but it's not always relevant for actually learning things. And this will interact with a statistical structure. This will interact with a causal structure in a variety of ways. So if you have time ordering, one benefit of this is that we can often use our strong physical knowledge or physical conjecture that time travels forwards, but not backwards, usually. I've tried to read several books on the physics of time travel, and my understanding is that it's a very interesting topic that's mostly not relevant for social science applications. We can generally rely on the fact that causal structure flows forward rather than backward in time. And so that is potentially a benefit. We know something about the ordering. So we've often implicitly used this when talking about causal ordering. We've talked about pre-treatment variables, post-treatment variables, and often suggested that, for example, things that are collected before treatment are also have the property that they are not downstream of the treatment in terms of the causal order. We were making use of the fact that that temporal ordering is informative for causal order. That said, once we have a dependent structure where these observations are related across each other, we, in terms of causal relationships, so if my actions today cause an outcome tomorrow that affects my actions tomorrow and 2 days in the future, then there's going to be, in general, statistical dependencies induced by these causal dependencies. However, the statistical properties of the observed variables and the counterfactual variables are, at least in principle, potentially distinct. So we may have potential outcomes that depend on the entire history, whereas the observed variables, because of the actual properties of the realizations, may have a more limited degree of temporal dependence. And so because our goal is usually to learn about these causal dependencies, we have to describe the statistical properties of both observed and counterfactual variables. And so this is a huge set of topics. You can talk about time series for, I teach a semester-long class on time series, and it doesn't nearly stretch to the range of possible topics. And so this is going to be basically just a few cases which are useful for causal inference, a few of the most salient facts. So we'll restrict attention to cases where finite sample inference is possible, and so we don't have to worry about some of these asymptotic issues. Or we have some potentially very strong assumptions made about dependence, and I'll talk briefly about what those are, that will allow us to rely on results that are pretty close to the results in the IID setting. And so this is something where it's not guaranteed. So if you work in finance or macro, arguably these assumptions are based on widely believed and reasonably well supported knowledge about the properties of financial and macroeconomic data. These assumptions may not be reasonable for financial and macro data, which is also the main class of applications for time series inference. That said, they're sometimes reasonable after appropriate transformations. And so today we're going to simply assume that these transformations have been made, and say if you don't do that, there be dragons, things can fall apart very easily. But I don't want to talk about unit root asymptotics, which is a fun topic that you could also teach, and I've taken a semester-long class on. Financial econometrics is a fun topic. So the other thing that we're going to focus on is a small set of causal models and a small set of causal estimands. And so as before, we'll focus on acyclic models. And so things like general equilibrium interactions are very interesting, central, again, to macro and finance. But at least for our discussions, we will postpone discussion of that. And the causal estimands will, aside from, I'll have one or two slides about what about interventions that affect more than a single point in time. Those will require a bit more work, and so we'll mostly focus on one thing at a time.
We also have time orders in some of the Canada data. Like the central side, the delta is small and the time is quite small. The frequency is quite big, and should use time series techniques instead of virtual Canada data.
So there is, I would say, a spectrum from time series to panel that you can think about, for example, a multivariate time series, or you can think of, a fairly long panel. And so these are observations where you have t time points, n variables, and the relative size of n versus t may describe whether it's more appropriate to use to think about it as time series or panel data. Formally, the kind of analysis that we're going to do with time series is, in terms of thinking, we're only going to be describing relationships within a variable or a small set of variables over time. And so the kinds of things that you can do with panel data are sometimes quite relevant. So some of these time series techniques will be used, and some of them that I'll get to are directly taken from the panel data literature. But the sort of unique challenge of time series is exactly this absence of repeated observations of, so if you have sort of, several people observed over a long period of time, you can assume that potentially their observations at any given period of time have a replicate, some sort of additional draw in the sample that you can use to learn about. And so here we're not letting us use that information, and so we're seeing what we can say just with the information with observations over time. But it's, in principle, these things are connected, and it's more how you analyze the data and sort of what sources of variation in the data you're using. So let's think about what kinds of applications you might want to really use this time series perspective. Exactly, its applications where you have data on outcomes where there are not necessarily comparable units. And so unlike in panel data, you can't rely on the fact that one unit got the treatment and another unit didn't, and then you can trace the dynamics of unit 1 versus unit 2. And so that would be a classic kind of technique that was the sort of analysis that we talked about in the panel data lecture with event studies and differences. Here, we don't have a unit 2, a control group to compare it to. And this is relevant, for example, in cases where our outcome is something like macroeconomic aggregates, because we all know that if you are a macroeconomist, the only country that exists in the world is the United States, and no other economy is comparable. Market level financial outcomes, if you're really interested particularly in the S&P 500, there is not another S&P 500 to compare it to. Things like geosciences, so human beings tend to care about the Earth and much less about other planets. We also have a lot more data on Earth than other planets. And so things like global climate modeling are another sort of application where you don't necessarily have comparable units, and you want to use the variation over time, the historical behavior of the same series as your set of comparisons. So for example, a macroeconomist who's interested in what's going on in the 2010s might think of a historical analogy to the 1930s, 40s, 50s, 60s, 70s, and so on. This can be used in things like panel data for performing comparisons within a unit observed repeatedly, so we can still think about panel data structure to the extent that, for example, there are differences across units that we don't necessarily know that much about. We can use the temporal structure within a unit to allow us to rely less on strong assumptions of comparability across units. So causal effects in time series can be across variables within a time series at the same time. So we can think, for example, of the impact of the Fed funds rate on asset prices in the same day. Maybe there's some temporal ordering, 2 seconds after the announcement. There's some changes, but often, and especially with macroeconomic aggregates, these things are recorded with a lag. They're temporally aggregated, meaning, so if you have something like GDP, this is the amount of production produced domestically, gross amount of production produced domestically within a time period, which might be a quarter. And so this adds up all the production over a quarter, and that is simultaneous with all the other economic activity, all the other variables occurring in that quarter. So in terms of the structure of the data that you receive, you may have things like GDP and government spending at the level of the quarter, or maybe you don't get GDP at the monthly level, but you get things like industrial production. And so to the extent that you're observing these things at the same frequency, they're effectively contemporaneous from the perspective of the data. And so you might be interested in contemporaneous effects. But you may also be interested in effects across time. So how does government spending affect not just current GDP, but the future path of GDP? If the government passes, let's say, an infrastructure bill, I think that passed sometime this week, what is that going to do to output, inflation, and so on?
Aren't these things GE though? Like, rate change by the Fed would have GE cyclic effects.
So that's a matter of modeling in some sense. So the sort of, is something GE, is the question of, is something better modeled by general equilibrium effects? Arguably, mostly yes. So a lot of these variables will be interested in at the level of temporal aggregation that we observe, simultaneous interactions. Now, for some of the ways that we're going to talk about based on acyclic models, we'll often be interested in things that, measures of treatment that we're getting potentially at higher frequency than these sort of temporally aggregated observations, where we might think that one thing genuinely does evolve autonomously, at least in part, and then outcomes respond to that. But then, maybe within the structure of outcomes, there may be simultaneity, but to the extent that our interest is in that vector of outcomes, and our treatment is not causally before that vector of outcomes, then we may be able to potentially rely on some of these techniques. And I'll get into quite a lot of detail with equations on when that's useful. You're right that GE is arguably key to a lot of modeling of these structures, and I basically said, yes, there's lots of topics I'm not going to cover. And so there's still some interesting things you can do in acyclic models, and I think it's worth spending a lecture on them. So how do we get these sorts of things that are not GE in the sense of, this is simultaneous with all the other variables in the system. So if we're thinking about macro aggregates, GDP, and so on, so we're interested in figuring out effects of government spending, effects of monetary policy shocks. So monetary policy, I'll hold off on explaining what a shock is. Both contemporaneously and over time, in order to think about sources of variation where we can isolate what that particular variable is doing, we'd like some random component or quasi-experimental component. And so these cases where these acyclic causal methods are particularly valuable are cases where we have historical accidents or idiosyncrasies not associated with, not simultaneously caused by, other sources of variation. And so this is something where if you just have, for example, GDP and government spending at the monthly or quarterly level, your hope of credibly estimating causal effects, at least without some strong causal assumptions, which probably would best be modeled by simultaneous relationships, is arguably fairly minimal. And so that was what a lot of macroeconometrics involved for quite a long time, probably at least until the 80s. More recently, people have been thinking about where we can find these sources of idiosyncratic variation, and this is usually based on institutional and historical understanding of the determinants of treatment. So the handbook chapter by Ramey that I posted on the syllabus as the suggested reading for this describes a lot of applications, in particular to this government spending and monetary policy questions, where they often make use of detailed narrative records of fiscal and monetary policymakers, as well as statistical properties, in order to isolate components of random variation. So think about, not just sort of what is the Federal Reserve's reaction function in general equilibrium, but also think about, for example, when precisely did Richard Nixon call Arthur Burns and tell him to do whatever he told him to do to the Fed funds rate, possibly using a bunch of curse words? If you've ever listened to the Nixon tapes, they're entertaining and inappropriate, and also relevant to isolating sources of variation in monetary policy that are non-systematic. Yeah.
Right, because I think sort of like, I don't know, I was listening to NPR last week and they were saying that after the Fed announced that they were going to start tapering, bond prices didn't move, so it's probably priced in. So that would, I guess, in this framework not be considered some sort of monetary shock.
Yeah, I'll actually talk about several of the examples of ways that people have measured monetary shocks. And so in particular, one of these sorts of things is, as with many of these cross-sectional sources of variation, it's often the case that there exist confounders for changes in the treatment. So changes in the treatment occur simultaneously with changes in other variables, and so we can't necessarily compare across them. And so to the extent that the state of the system was not comparable, say before and after, then we might not want to interpret this Fed effect so the before and after change of this monetary policy announcement as being from something that was due to random variation. And we have ways of accounting for that, including things that will look like adjustment. And so in fact, I'll talk about cases where we do have random variation, cases where we only have conditional random variation, which will allow us to perform adjustment, as well as a couple of other methods. So first, we need to describe what are the statistical properties of time series that we have to deal with whenever we're trying to answer these questions. So our time series of variables, OT, from t equals 1 to capital T, is something that we're going to model as a stochastic process. This is a sequence of random variables indexed by t. So we can think about this as that these all live on the same probability space, and they have some joint distribution. And so, introducing some notation, so we will refer to relationships between variables by adjustments in the index. So OT minus 1 will be referred to as the lag of OT. And so this might be for an arbitrary index T. This is whatever happened the period before. We'll use a superscript, O superscript T, to indicate the entire history from period T back until the beginning of the time series. So note that although I'm describing this as 1 to cap T, in some of the cases that we're going to deal with, it may be more appropriate to think about the final period being infinite, and period 1 potentially being arbitrarily far in the past. For the finite sample components, analysis, we won't necessarily have infinite data, but often the statistical model of that data will be that these are some subsequence of a larger observation, larger, potentially infinite sequence. And so we will denote subsequences with a subscript S colon T, so OS colon T, which will correspond to just the observations between S and T. And so our goal is often going to be to extrapolate from past to future values. And so the most common framework that will allow us to do this, modeling assumption, is what's known as stationarity. And so in words, what this refers to is the situation that historical patterns are assumed to be identical in distribution to patterns at other times. So we can think about the subsequence, for example, in the 1940s, as comparable, so not identical to, but drawn from the same distribution as the subsequence in the 1950s, the 1980s, and the 2010s. And so formally, a time series OT t equals 1 to t is what's referred to as strictly stationary if for any subsequence of the time series. So if we have OT subscript j for j equals 1 to j, so this is any collection of time periods, so March 2013, January 1917, so on. If we shift them uniformly by an amount h in time, so if we shift tj to tj minus h, so if we shift March 2013 to January 2013, 2 months back, and we also shift January 2017 to November 2016, the joint distribution of the subsequence of the first subsequence is equal to the joint distribution of the shifted subsequence. And so only the distance in time between observations affects their relationship, not the identity of the time point. And so this is a very strong assumption. It rolls out series that are trending up or down. So the level of the time series then would depend on the identity of the time point. It rolls out shifts or breaks after which the distribution changes. So lots of classic examples of that where policy changes dramatically at some point, and then the statistical behavior over short time periods of a series changes. Things like predictable seasonal changes, then whether the quarter is divisible by, so you divide that by 4, so whether you're in fall, winter, spring will matter for the value of the series. So almost all macroeconomic series, aside from a few policy things that are set artificially, have pronounced seasonality. Systematic changes in variability, this is actually a hard one. If something is wandering around over time, accumulating the impact of past shocks, then to the extent that these things add up, it becomes more and more variable, and so the distribution is changing. And so this is typical of, for example, financial asset prices. So in general, data doesn't come to you stationary. It's not something that you want to assume. It may only be stationary after transforming it. And there are various ways to do this depending on the type of non-stationarity that you have to be aware of or able to deal with. So a classic example is if yt is increasing by c units each period. So let's say this is, log macroeconomic series. Log GDP is increasing by 2%. GDP is increasing by 2% per year. The log is increasing by an amount, by a fixed amount. Subtracting out the trend might then restore the level to being comparable over time after what's known as detrending. And so there are various, for all of these sorts of non-stationarity, there's detrending, there's deseasonalization, there's break removal, and so on. And this is an important part of sort of the data preparation that you have to do whenever you're working with time series, if you're going to rely on methods that assume stationarity. If we have it, which usually we don't, but occasionally we can approximate it after transformations, it will allow us to say something about the full series from only part of it, because we can take, for example, the distribution of observations at time t, or their expectation, or the conditional distribution at time t given the past, the history, so O subscript t given O superscript t, as quantities which do not depend on t. And so this is something where I'll use the t index, but the actual value of the t won't matter. That will be the same for any t. And so we can think about the distribution of an observation or a vector, or the conditional distribution of a pair or a subsequence of time points. This is related to, but distinct to, time invariance of the causal structure. So to the extent that there is a directed acyclic graph, a structural causal model relating OT and its history, we might have a time invariant causal structure if the form of the relationships, so these functions and the graph, do not depend on t. And so this is the kind of thing where if that's the case, the causal structure of, say, x1 causing x today causing y tomorrow, so there being a causal arrow in that direction, will be replicated between x today and y tomorrow, and x tomorrow and y the day after, and so on. And so this will imply, to the extent that you have a time invariant structural causal model, a time invariant set of conditional distributions. So fixing the variables in one time period in the directed acyclic graph, and assuming already here that these are sort of ordered only forwards in time, that will imply that the observed and conditional distributions are not changing with time. This is necessary but not sufficient for statistical stationarity. So you can have, for example, a trending series where the outcome is growing by the same amount each period. And so that would be something where the conditional distribution is time invariant. It's whatever it was plus 2, was in the past plus 2, but it's not statistically stationary. And so for most causal estimands, we're going to be relying on stationarity of both observed and counterfactual outcomes, and so this will require both causal time invariance as well as statistical time invariance, and potentially the stronger property of statistical stationarity. So that even allows us to define the distribution, for example, what is the causal effect of a monetary shock on GDP? we can say that that has a distribution which is independent of, say, the causal effect of a monetary shock on GDP in 2021 versus the causal effect of a monetary shock in 1975. We need more than this, unfortunately. So if we're going to estimate these distributions and not just rely on the fact that they exist, it would help to have versions of the inferential tools, estimation tools that we rely on for most statistical estimation in cross-sectional data, and in particular the law of large numbers and central limit theorem would be nice things to have if we can say that averages over time converge to something and they tell us the distribution, because this is the main way we learn distributions in cross sections. This requires stationarity or something like it. So sometimes we replace strict stationarity with just stationarity of the parts that are relevant to the thing that we're estimating. But for now, let's just think about strict stationarity. But that's not enough. So to see why that's not enough, consider a stochastic process which can take on two possible sequences of values, either 0, 0, 0 indefinitely for all time, and it takes on this set of values with probability 1/2, or 1, 1, 1 indefinitely for all time, taking on that set of values with probability 1/2. This is stationary according to the definition that we described before. The expectation of any observation is 0.5. That's time invariant. If we take the sample average, with probability 1, it will be bounded away from 0.5. It will either be 0 or it will either be 1. And so this suggests that although it has a time invariant average, we can't learn about it by taking sample averages. The condition which says that we can do this, so time series that do have the property that sample averages converge in probability to the expectation are referred to as ergodic. And so the version of the law of large numbers that applies for these time series is called the ergodic theorem. There are actually many ergodic theorems, so maybe we should say unergodic theorem in the same way that there are many laws of large numbers. So there's a variety of sufficient conditions for this that are fun to study. They depend on various models of the time series. But rather than going through those in detail, I'll say that if we want to not just have consistency but also perform inference, we might want a central limit theorem or something like it, which will require even stronger conditions than this. So let's talk mostly about the stronger conditions. And these conditions basically ensure that dependence, so measures of correlation, covariance, or other measures of statistical relationship across time, decay to 0 as the temporal distance between observations goes to infinity. So formally, I'm sorry to do this, but I'm going to introduce a sigma algebra. So let F subscript S superscript T be the space of events generated by the observations between S and T. So let's think about all possible, functions, or OS is is equal to 1, OS plus 1 is equal to 2, and so on would be an event between those. And here, let's allow S and T possibly to be infinite. I'm glossing over a huge amount of technicalities when you deal with, infinite sigma fields and all of that are, again, fun to study, not super relevant for what we're doing. There are theorems that say it all works. So formally, what we can do is, so here's a way of measuring dependence. Take two events, A and B, where A depends on the time series from the start up to time t, and B depends on the time series from time t plus j to the end. So these are two events separated in time by amount j. And consider the probability of the intersection of those events. If they were completely independent, it would equal the product of the probabilities of those events. And if they're approximately independent, then the difference in the probability of the intersection and the product of the probabilities would be small. That's one way of saying that we're approximately independent. If we take the supremum over all possible events, separated by j apart, of this measure of distance from independence, we get the coefficient alpha j, which note that if we're assuming stationarity, it doesn't depend on what t is, just the separation in time. And so this is called the alpha mixing coefficient. And so formally what we would like to sort of say that as we get more data, the observations become approximately independent, is that these mixing coefficients go to 0 as time increases. So we call a series with this property alpha mixing or strong mixing, though the word strong mixing has several mathematically non-equivalent definitions that are ambiguous. So the idea behind this, so this particular dependence measure is not that important, but the idea that we're going to want is that as we get further separated in time, points are closer and closer to independent. Yeah?
Can you give some sort of intuition from what that
Sure.
is?
So the alpha mixing coefficient is bounded by the rho mixing coefficient, which is, so that doesn't sound like intuition, but I'll go on, which is the covariance between any two events. And so this is like, we think about the covariance between GDP in 1945 and GDP in 1999, 50 years of, 54 years apart. We would expect that to be pretty close to 0. If we take two events and they're 2 years apart, they may be correlated. So there's going to be something going on that this process just lasts a little while. If you're in a recession in 1947, 48, somewhere there was a recession like late 40s. What does that say about your chance of a recession in 1995? And if you have this sort of stationarity property, it should be the case that 50 years later, the precise whether you're in a recession or not is, if you knew that you were in a recession in 1948, should tell you almost nothing about whether you're in a recession in 1995. So that's the idea. And so tell you almost nothing about is formalized by some measure of statistical dependence. And it can be covariance that gives you rho mixing. It can be total variation distance that gives you beta mixing, or it can be this distance between the intersection and the product, which gives you alpha mixing.
So is this supremum taken over T?
Sorry, the supremum is taken over events A and B.
I see.
So this is like, there could be some events that, the product just happens to work out, and so this is sort of a strong measure. It says any variable that you can think of. And so in principle, this is stronger than we'll need because we're only going to be dealing with, whichever variables go into our estimators. And so sometimes people work with measures of dependence that are sort of less restricted, but this is a nice sufficient condition. It says no matter what variable you're working with, they're not going to be strongly dependent. It actually, for many things, it's too strong. So you can come up with, so sort of time series models very often have this property if they don't have trends or sort of wandering behavior. But in principle, you can rule it out. So we have books from the 1940s to the extent, for example, that information that gets written down in a book can be read today and affect actions today, then any sort of statistical event of that form will be informative for what happens today. And so at the level of, are the laws of physics strong mixing? Potentially. I think there's some Newtonian physics might be ergodic, which is to say that like over the span of the universe, if you go for a long period of time, in practice for social science events, it's going to be relevant to whichever kinds of events we're going to measure. So you can sort of break this by saying, I wrote down a number in a book, and then 50 years later, I opened up that book and I chose that particular number. If that's the event you're trying to measure, that would be the sort of worst case correlation event. This is just sort of a sufficient condition. You really only need this for the things you're trying to measure. Anyway, the point of it is just that you want to bound the covariances over time in order to get a central limit theorem. Primitive conditions for this depend on your model of the stochastic process. It's by no means guaranteed. For linear relationships, it often requires bounds on the coefficients. For nonlinear relationships, functional form restrictions. And the precise conditions for that I'm not going to get into. So inference. So suppose we have a stationary and ergodic series, YT, and it has 2R moments, so expectation of Y to the 2R is finite for some R greater than 1, and it's alpha mixing with some bound on the sum of the alpha mixing coefficients. So these are summable with product 1 over K R minus 1, so this is like just decaying to 0 at a particular speed. So this is sort of polynomially fast depending on the existence of moments. Then you get a central limit theorem for the time series. So the sample average scaled by square root t and the mean converges in distribution to a normal. And so this is kind of the nice thing that you would expect that would rely on for IAD data. The thing that differs is that the sigma is what's referred to as the long run variance. And so the idea behind this is that a sample average, if we take the variance of a sample average, where observations are correlated over time, so YT and YT plus 1, YT and YT plus 2, the variance of the sum equals the sum of the variances plus the sum of all the covariances across units. And so if we take the limit, that variance of the sum will depend on the sum of the covariances from all the way in the past to all the way in the future, h equals negative infinity to positive infinity of the covariance between YT and YT plus h. Or if we have stationarity, so sorry, we don't need stationarity for this. This is just by symmetry. Well, no, this will rely on the fact that only sort of distance and time matters. The variance of YT plus 2 times the sum of the covariances, often to the future. So the particular moment conditions are from Ducombe, Massart, and Riot, but basically the idea behind it is that this mixing is you need something slightly stronger than this long run variance being finite. And so you need the covariances to decay to zero sufficiently fast such that this is summable. Otherwise, you're not going to get convergence to something with a finite variance. So in practice, the thing that you have to do with this is estimate this variance if you're ever going to compute standard errors for your estimators. And so typically what we do is we use a possibly kernel-weighted sum of the sample covariances. We call these the auto covariances of Y, so covariance with itself. And so this is, we get the sample variance plus some sum from the kernel times the sample covariance, where this kernel might be something like Nui West suggested triangular kernel, 1 minus absolute value of U, with so H over S for H units apart. And so the idea is that you downweight units that are further away. And part of the reason for this is so if you have T observations, you only have 2 observations that are T apart in your sample. And so these sort of higher order ones are not estimated particularly well. You need some conditions on the bandwidth for this to be consistent. In fact, you actually also need stronger moment and dependence conditions in order to consistently estimate this, because you have to get the variances across different times. And so even though I gave you some moment and mixing conditions, you need higher moment conditions and faster mixing in order to consistently estimate this variance. Rule of thumb is about bandwidth should be 3/4 T to the 1/3. That's in standard textbooks. A lot of the literature on this, there's a huge literature on estimating these variances. Notes that because this is like a non-parametric kernel-weighted thing, there's an infinite number of things to estimate. It actually, so technically all you need is consistency. But if you're going to construct a t-test, because this is going to be estimated really poorly, it converges at a slow rate. In finite samples, your inference will be distorted, potentially quite a lot. And so people have, so in the same way that for t-tests, you might use a t-distribution as opposed to a normal distribution to account for the variability in your estimates. You need that sort of on steroids, but the actual distributions are quite nasty in most cases. And so there's a lot of complicated literature, and nobody ever uses it because Nui West is in Stata and every other software package. And so everybody just uses Nui West, and nobody will ever question you on it, even though time series econometricians have been yelling for 30 years since then that the inference properties of that are only so-so. Alternate approaches, so rather than mixing, you can build the series out of some combinations of independent components. There are various types of central limit theorems that do that. Martingale, CLTs, Martingale measure, math is important in finance. It's worth knowing. Sorry, finance people. I do a lot of work with martingales, but okay, what if you don't have stationarity in mixing? You don't necessarily get a CLT. So the most common case is integrated processes where YT is not stationary, but YT minus 1, the change is stationary. Asset prices typically satisfy this property, or approximately satisfy this property. Anything linked to the level of asset prices typically satisfies this property. Basically, so if you believe the fundamental theorem of asset pricing, more or less with transformations, asset prices should look like this, and if something looks like this, you can't rely on these conditions, but potentially you can for the differences. And so general rule of thumb, anything I'm saying, apply at tacit returns, not tacit prices, or else everything will blow up in interesting ways. Okay, that was longer than I expected to take on the statistical aspects. So now let's get to the causal aspects. Fortunately, a lot of these slides are filled up with big DAGs, so a lot of drawings. So our target will be to measure the effect of a treatment variable xt at a point in time t on an outcome variable yt plus h, some point h in the future. For now, we won't be assuming most of the results that I'm going to describe don't necessarily require this stationarity and mixing. Though once we get to estimation, we'll say, okay, this is defined in terms of the distribution, but how do you estimate it? Well, then you may need to impose something like that. And so our target is to measure the sequence of effects as a function of h, to trace out the time path of, if, let's say, if the Fed increases the Fed funds rate, what is going to be the impact on GDP this month, next month, the following month, and so on. This function is called the impulse response function to the shock or the change, or the causal impulse response function. So this is taken from the engineering literature. So especially relative to the other topics that we've studied, time series literature has focused on parametric, homogeneous linear models of effects. And so much less is known about heterogeneous effects, the sort of general potential outcomes framework that has been changing how we think about experiments, instrumental variables, difference in differences, and so on. That sort of transformation is less far along in time series. And part of the problem is that allowing very general forms results in an exponentially growing number of arguments to some of your functions, because you have, so if a binary treatment can take on different values over a sequence of time periods, then over k time periods, you have 2 to the k possible assignments of that binary treatment. And so being fully general in these situations requires a lot of notation, as well as just sort of being hard to estimate. And so I'm going to give you some results from a recent working paper by Rambachan and Shepard, which tries to think through some of these conditions for identification, in the sense of relating the potential outcomes distribution to some features of the probability distribution of the observed variables, which may or may not imply consistency. But they do it for some useful special cases, and so I'm going to be following them. They don't assume stationarity in their results, though once you get to estimation, it will help to impose it. And in fact, with estimation, we'll talk about simplifications, because in practice, people basically use things that are variants of ordinary least squares. And so we'll talk about sort of what is the corresponding OLS regression that people run in practice that may or may not have a causal interpretation. And so we assume a treatment process xt, dx dimensional, t equals 1 to t, outcome process yt, t equals 1 to t, dy dimensional, and we'll have potential outcomes where yt depends on the entire sequence of xt. So x1 to t equals little x 1 to t. So recall that this is the notation for a sequence of treatments. And we'll impose a few assumptions that are the time series versions of the standard assumptions for treatment effect estimation. So causal consistency is the usual one that if we see an x, a sequence of x's, and we see a y, then the y that we've observed is equal to the potential outcomes given that the treatments are assigned to the actual values that we saw. The time series structure that we're going to use is going to say that, so if we think that treatments don't have an effect backwards in time, only forwards in time, then we can impose that x to the 1 to little t is the potential outcome for the time series path of treatments up to the present time, and then also the future time, but the future time will be arbitrary. And so differences in the future time will not affect the potential outcome. Future treatments will not affect the potential outcome presently. So this is called non-anticipation because we're thinking about, so when would this be ruled out? So time travel is sort of a fanciful one. In practice, the thing that you want to worry about is that you have some unobserved variables which allow people to anticipate what the treatment path is going to be. And so it's not that, well, maybe they have ESP, but more likely they have the ability to think about what's going to happen in the future and some information about that you're not accounting for. So this is really what we're ruling out. And then we'll need an overlap condition to estimate, or in order to be able to even define all the conditional probabilities. And so they focus in the Ramachan and Shepard paper on the potential outcomes corresponding to changing xk, which is the kth element of xt in period t. And so changing one element of the vector of treatments at a particular time, but the potential outcomes, so leaving all the other x's, both past and future, the same. I'll denote this y superscript xt in parentheses to distinguish it from y given do xtk equals little xk, which might have effects on other variables. And so their goal for their definition of an IRF is the difference between yxk parenthesis minus yx prime k parenthesis. So changing just this one element just at this one point of time and leaving everything else the same. What does that do to the average y? So one thing that you might want to do is the difference in means estimator. It's a classic. You might think, so what is the difference between, raising the Fed funds rate to not? Take the difference in averages between whether they raised the Fed funds rate or didn't. So conditional on that xkt. So they have a treatment plus selection bias decomposition for this causal estimand. So this difference in means equals the causal effect, the IRF that they're describing, plus the difference in, so the covariance of y with the treatment divided by the expectation of the indicator of the treatment taking on a particular value divided by the probability it takes on that particular value, the difference of that between the two treatment values. And so the idea is that if raising the Fed funds rate is associated with differences in the potential outcome, then the difference in means will not be a causal effect. And the proof of this, so expectation of y times an indicator of getting treatment xk is under causal consistency, so that is exactly the y that we see. So that's equal to the potential outcome for the y that we would see given xt kt equals xk. And then the definition of covariance is the expectation of the product minus the product of the expectation. So we add on to that product of the expectations, we get this expectation of the product. Now, if we divide both sides by the probability of the treatment, on the left-hand side here, applying the inverse propensity lemma, we get the conditional expectation of the outcome given the treatment. And on the right-hand side, we get this covariance. So we get so the expectation here of the potential outcome, that's what we want to measure, plus this covariance term, which represents the selection bias. And so this difference in means estimator for the IRF is not going to identify the causal effect unless we can say that this covariance is 0. So when would that be true? Well, in the presence of a repeated experiment. So when so each period x is assigned with no incoming arrows, so it's randomly assigned. Corollary to that, if xkt is independent of the potential outcomes in all periods and all treatments, past, future, and other values of the treatment aside from xk in the present. So this is exactly when each period you have a randomized trial, independent of all previous randomized trials, then this covariance will be 0. And the difference in means will equal the IRF. So the sort of thing that's unique to the time series process is that because we have this repeatedly, so we do allow y to have effects over time. That's fine. So this is in fact how we think the dynamics might occur. So through the changes in y might have a series of processes as well as potentially direct effects of the x on our future values. That's also unrestricted. But we can't have any interactions among the treatments, either past or future, because the future treatments are part of the determinants of y as well as the past ones. And so the sort of repeated IID experiment is a very weird setting that, sometimes in a lab it might exist. Often we want to think about this not so much as like really something that we'll see, but as a model for the effects of, we can think about the independent components, the temporally independent components of treatment. And so sometimes we call such temporally independent, temporally and causally independent variations in the treatment structural shocks. So this is something that we in structural models often build our structural model where variables are determined by many things, but the variation in them is ultimately attributable to components which have some sort of independence property like this. And so to the extent that we can, usually what we're going to do is not actually have observations of shocks like this, but what we're going to do is think about this as the sort of model for comparison in the same way that a cross-sectional experiment is our model for comparison in the cross-sectional data. A shock of this form is sort of our model of comparison for time series dependence. So if we had this, we could just use a difference in means. The difference in means gives us the average treatment effect, so the average IRF. We may be interested in conditional effects, so conditional, for example, on the past, so the history of X and Y. And so just the estimate, the statistical estimand there is the difference in conditional means, given that the treatment is assigned to xk, xkt is assigned to some value little xk, conditional on the past, and we look at these difference in means conditional on the past. And so a conditional version of the above proof applies mutatis mutandis, just conditioning, just adding conditioning in all of these variables. We get that this difference in conditional means is equal to the conditional causal effect plus this difference in conditional covariances. And so if we have that conditional on the past, our treatment is assigned independent of potential outcomes. So the observed potential outcomes and future potential outcomes, as well as future treatment assignments, then these covariances are zero. So recall that this yx in parentheses corresponds to changing just x, but leaving the path of future x's unchanged. And so in general, to the extent that our treatment assignment is correlated with future treatment assignments, it will be correlated with y superscript parenthesis xk. And so this, the idea behind it is that controlling for history will allow us to measure conditional causal effects. This will in general fail if each assignment depends on past outcomes. And so difference in conditional means is not enough to measure this causal conditional IRF of sort of just changing the treatment at one time. This is often something that's computed in structural models. Often we just have the shocks that we've built up in our macro model. If your model is nonlinear, to compute these impulse responses, you want to do this conditional on the past values to the extent that there's some dependence of the causal effect on the actual current values of these things. And so this is the kind of thing that if you have a nonlinear macro model, you'll compute these generalized IRFs by simulation. So this is something where sort of getting the comparison, so often you don't, so conditional means you'll want to fix the conditional, fix the xk and take the conditional mean given the past values. Computation-wise, people often do strange things when they're summarizing the impulse response functions from their nonlinear dynamic models. This is arguably a causally interpretable component that you would maybe want to compare to data. Now, what can we actually get? So suppose we have sequential conditional random assignment. So for now, I'm just going to talk about x's and y's. And so conditioning just on the past. In general, even if we just have treatments and outcomes, treatment assignment will generally depend on the history of the system. So there's going to be dependence on the history of both treatment and outcome values. So look at this horrible tangle of a DAG. This is just sort of a subsequence of the DAG if we want to think about this extending even further. So what we're going to allow is that x and y to depend on all past variables, not just sort of the past treatment, the past outcome, but all past treatments, all past outcomes. And so a causal effect of a change in x, we can think about many of them. We could think about this causal effect of a change in x holding the future x's at what they would have been without it. But if we think of just doing, say, xt equals, little x, then that will have a causal effect on both future treatment assignments, and future outcomes. And so the potential outcome that we'll measure is yt plus h given x1 to t minus 1, little xt, and then the x's that we'll see are themselves the potential outcomes, so x superscript xt from t plus 1 to t plus h. And so that contains both the impact of the current treatment change as well as the impact of changes in future treatment assignment. If this is the object of interest and we observe the relevant history, then we can apply the adjustment formula. So by conditional ignorability, so if we have conditional ignorability, if this y superscript x not in parentheses, which corresponds to changing all things that would change if we changed xt, we can account for this by applying standard adjustment. So there's generalized IRF, which is the conditional difference in means, will equal the conditional causal effect. And then under overlap, this will be defined, so the probability of treatment assignments will be defined, and we can average over this to get the causal impulse response, changing a treatment and letting all the future treatments and outcomes be affected. So this is actually what we usually get by applying an adjustment type formula, and sort of preview the way we're going to apply an adjustment formula. Or let me rephrase this. The way other people usually apply an adjustment formula is linear regression. So they'll regress yt plus h on the treatment and a set of controls. And that's what you're getting here. So adjustment measures a form of this IRF, which contains both the outcome and the policy responses to treatment. So for example, if monetary policy mistakes are followed by subsequent reversals, we're not measuring sort of just the effect of, say, contractionary monetary policy or expansionary monetary policy, because so if part of the response to let's say, expansionary monetary policy is for the Fed to think, no, wait, we didn't want to do this, and then afterwards apply contractionary monetary policy, then you're getting the effect of that full sequence, which may or may not be what you want to estimate. So this will be, I'll show you some estimates from measures like this. So conditional random assignment, I described this, I drew a DAG, and then I gave you a condition in terms of potential outcomes. What we'd really like is a condition in terms of the DAG. So helpful trick for verifying this. This is something, so it's described in the Ernan and Robbins book. The original paper by Richardson and Robbins is like 150 pages long and nigh unreadable. But the actual trick is super easy to use. It puts the potential outcomes and the observed outcomes on the same graph that they call a single world intervention graph, or SWIG. And so this is just a tool for verifying relationships between observed and potential outcomes. And so the idea behind it is that one way you can represent the do operation is by, so we talked about it before, as creating a completely new graph where the arrows into your treatment variable are deleted, but then you have two graphs that you need to sort of compare across them. So what a SWIG does is they put them on the same graph, but they split the treatment node. So in this case, say our treatment node is x2, we split it into x2, the observed value, and x2, the value that we do, the counterfactual outcome. And so we make two nodes that are linked together. And so descendants of the split node are the potential outcomes, the counterfactuals. And then the things that are not descendants are the observed values. And so we can do things, because this graph will obey the causal Markov property, we can measure, say, dependency between observed and counterfactual outcomes, which is what we need for adjustment formulas, by applying deseparation. So if we want to verify that y superscript x, the potential outcome of y given x, is independent of observed x given z, that's true if yx is deseparated from x given z in the SWIG G. And so this is something where, because these lie on the same graph, we can just check that. So here, this is just a 3-period version of sequential setting from before. If we split x, the arrows going into x2 we still have. So we still know what the properties of x2 are, but the arrows coming out of x2 are then changed to counterfactual node, and we see the counterfactuals for x3, y2, and y3. And so if we want to know if present and future y are conditionally independent of potential outcomes are conditionally independent of the observed x, we can just check whether these are d-separated. And so rather than doing that by hand, we can software do this for us. So I was going through these last night, and the proofs in that Rambachan and Shepard paper are very annoying and basically only applicable in the sequential experiment setting. This DAG describing things in terms of potential outcomes is nasty. And so I went and I just drew a bunch of swigs, and the proofs are like one line if you're willing to let yourself rely on d-separation. Aside on what needs to be controlled for, so what do we include in our structural causal model? Economic reasoning will help. So in general, a forward-looking decision maker who cares about outcomes will use expectations of future outcomes to determine actions. So think, the Fed chair is thinking about what's going to happen to the economy if they change interest rates. As a result of that, any past variable known to the decision maker which predicts the outcome within the planning horizon is likely or may impact their predictions and so their decisions. And so what that means is that it's very hard to exclude almost any past observable variable from the adjustment set if we're thinking about economic policy, even if it's not something that, do we think that the policymaker directly cares about it? Well, they care about it to the extent that it impacts the future value. And so anything that's sort of economically relevant or going to be economically relevant to the future should be considered as, part of the determinants. And so it also means that the kind of confounders we should worry about are sources of information that the decision makers have that aren't in our data set, such as news about developments affecting the outcome. And so if there's sort of news that's going on, so if the Fed gets some news that there's going to be a recession, and because of that they cut interest rates, and we don't have that news in our data set, then it will look like they cut interest rates and then afterwards there is a recession. That's not necessarily a measure of the causal effect. So this is just a standard sort of confounding issue. And so it's common to use, so how do we incorporate as much of that information as possible, or that public information? Well, a lot of it gets incorporated into asset prices. So there's a Fed funds futures market where everybody competes to predict what the Fed funds rate is going to be. And so anything that's going to be potentially relevant for the treatment assignment is, many things are likely to be priced in to the futures market. And so this is since Kuttner 2001, sort of a de rigueur to control to include if you're trying to measure the effects of monetary policy decisions. Of course, pricing is complicated, and the price of a future is a single value, and potentially there are other things going into it. So it's not necessarily fully predictive, but it has a lot of predictive power. Nakamura and Steinson use sort of very high frequency, so up to what is the Fed funds future price 5 minutes before the announcement, to try and get as much information as possible. Official forecasts, surveys, media, take the Wall Street Journal on that day and do your text analysis to make sure that the reason they're changing interest rates is not because there was some huge problem in a particular bank that blew up, And then that may be actually what's causing the changes and not necessarily some autonomous variation. Databases of macroeconomic variables, so just sort of everything that's publicly available, we include. Rational expectations is sort of a stronger version of this. It's a modeling framework for deriving expectations from the model implied law of the data. Then often it's assumed that we have optimization is how they make those decisions. This is a framework which naturally leads you to worry about these sort of confounders, and they may help suggest covariates and even functional forms. They're not needed when applying non or semi-parametric inference methods to the extent that you're accounting for the sources of variation. It's also the case that pure optimization as a model is a little bit inconsistent with the ability to have overlap, so non-systematic variation in the treatment assignment, unless there's some additional sources of idiosyncratic variation in the treatment, not due to economically relevant factors, but things like mistakes or changes in taste of policymakers or misperceptions. And so sort of looking at the historical record and what were Paul Volcker or Alan Greenspan thinking that day is sort of very relevant, this kind of modeling. So another simplification, so sometimes rather than this huge tangle, we say that things depend not on the full past, but on the most recent past. We call this, we call such a process Markovian, or we say that the causal structure is recursive. So we deseparate the current values from the history. Sorry, this should be OT plus 1 is deseparated from OT minus 1, given the current value, from O is deseparated from the history given the current value. And so this also implies, so the statistical version of this is the Markov condition that OT plus 1, given the history up to OT, actually depends only on the values at T and not any any further past values. So this simplifies your analysis enormously. Large fraction of dynamic economic modeling, Youngquist and Sargent textbooks, Stokey, Lucas, and Prescott textbook. If you took a macro class, you used one of these or a book that was heavily derived from one of them. You can truncate the conditional ignorability to just depend on the most recent past values. So this should be given xt minus 1. So these should all be minus 1s for this. And likewise, the generalized IRF, so you just depend on sort of the most recent values describing the state. So you can extend this to k-period dependence by simply defining as parts of the state the most recent k periods of values. And then for the current value, you have the law of motion for, so one period ahead. And then for the difference between, say, t minus 1 and t minus 2, well, you just shift that out. T minus 1 today is the t minus 2 of tomorrow. And so this is sometimes called the companion form of the law of motion, and it allows you to write higher order Markov processes as first order Markov processes. So that's in some ways without loss of generality. So estimation, finally getting to this. How do we estimate this? So if the probability of assignment is known, we can construct an unbiased estimator in the case of repeated random or conditionally random assignment by inverse propensity weighting. So we multiply yt plus h by indicator that the treatment took on value x divided by the probability that it would have taken value x given. So if we have conditional random assignment given the past values, if we have unconditional random assignment, just the inverse propensity. And this will equal in expectation the conditional mean. And so this is something that can be defined without stationarity. We can get the effects of the intervention at time t by this, just this inverse propensity weight at time t. Without stationarity, the effect of the intervention at time t may not be the same as the effect of the intervention at other times. But you can aggregate, you can take the sample average of the inverse propensity weighted y's over t equals 1 to t minus h. If you have, so because you need yt plus h, so you can't get the future values beyond what's in your data set. And this will get you an unbiased estimate of the time average of the period t IRF. So each period t IRF is different, but potentially you can get sort of the average of all of these different IRFs. You can aggregate over them. With stationarity, and you're unbiased there, you're not consistent without stationarity because it's, this object doesn't even necessarily, you know, there's nothing to be consistent for. With stationarity of the treatments and potential and observed outcomes, I just wrote that as potential outcomes because observed follows by causal consistency. This is an unbiased estimate of the population average treatment effect. And then adding on to stationarity, ergodicity and strong mixing, appropriate rates, you can get consistency and asymptotic normality for this estimator. Finite and appropriate bounds for the conditional variance on the summands of the variance as well. This is actually slightly more delicate than just assuming that the x's and y's have are stationary and mixing, because this, so especially this propensity score may depend on past values, and so this is a function of sort of many time periods, and that potentially needs to be stationary or mixing. In the finite order Markovian case, you can basically, you can bound the mixing coefficients for, you know, if you're 2 periods apart, if you're 10 periods apart, but you have sort of one lag in included in your conditional probability, well, the lags are 9 periods apart, and so you can use the sort of mixing coefficients there. In the case where you need to depend on the whole past, the analysis becomes more delicate, even if the x's and y's are stationary and mixing, because the entire past goes into the propensity score, and that induces statistical dependence between the components of the estimand. And so you can do this if you bound the magnitude of the causal effects of the history on the treatment assignment in appropriate ways. So a really strong bound is the Markovian case, where it's bounded by 0 after a few lags, but you can get away with something slightly weaker. So if you know the propensity score, that's great. Of course, you usually don't. In the stationary ergodic case, mixing case, you can estimate it, e.g. by a parametric model, probit, logit, etc. Angrist, Jorda, and Kirsteiner describe properties of this IPW estimation for time series, for stationarity and mixing. Alternately, you can estimate the difference in conditional means directly. If you do this by linear regression of yt plus h on xtk, possibly with controls, that's called a local projection estimator. And the Ramey survey describes uses of this in macroeconomics. Rombachon and Shepard show that, so in the general potential outcome case, you can treat this linear estimate with covariance of yx over variance of xt as a weighted average, particular weighted average of treatment effects. Nothing is stopping you from running just the standard AIPW estimator with conditional mean and conditional probability estimates. I haven't actually been able to find much in the time series literature on people doing this. So there's a few people who have done it in sequential settings that are not the sort of stationary mixing setting of, this Angrist, Jordan, Kirsteiner paper is quite recent even for IPW. But it's easy to verify that it's doubly robust in the identification sense. So if either is correctly specified, the expectation will be the correct thing. If you're going to try cross-fitting for this in time series, so because these observations aren't IID, you can't choose the observations at random. So we use something called blocking. So it's just we take the observations in blocks. So the first third, the second third, the third third. We throw out the middle third, just so that if we have mixing, the first and the third parts will then be close to independent in appropriate sense, and so we can rely on this sort of approximate independence. And then we can fit the nuisances on the first, and then the estimator on the third, and then switch. So this is something that this Cato paper does that, but not quite in the same setting. And so this allows us to get some sort of analog of this. This has to have been done somewhere on the literature, but if not, somebody please write that paper. Here's the Angrist, Jordan, Kirsteiner results using IPW. You get the effect of the Fed funds rate on economic variables. Here, industrial production is, you don't get GDP by month, but you do get industrial output by month. And they use Fed funds futures as controls as well as past rates and economic aggregates to incorporate market predictions into the rule. Here's the time series of propensity scores. We see that these vary with economic conditions, and then the actual outcomes are the dots. We see that the Fed either raises or lowers rates in sort of a much more discrete fashion. And then the blue time series is industrial production. That's the outcome that they're trying to measure. And we see, for example, that in some periods, there's sort of higher probabilities of rate hikes. In some periods, there's higher probabilities of rate cuts. But these sort of vary relative to the actual outcomes. And so these are their results for the IRFs. They find asymmetric effects for rate increases and decreases, which is, you can get that from IPW and not from linear estimators, which impose a functional form in the outcome model. And so the direction of effects is consistent with conventional wisdom, but the asymmetry, they find that rate hikes have stronger effects on output, inflation, and so on than rate increases. So part of this, it seems to be, is recall that you're measuring the effects of a point-in-time treatment, which may affect future treatment values. So part of this is also that the response to a rate hike seems to be, so they measure that as you get a continued sequence of increasing rate hikes, whereas the response to a rate cut doesn't seem to be in this data followed by an increasing sequence of rate cuts. So this is sort of, we should think about this as the effect of the full-time path of treatments induced by a point in time. So how do we do this in the linear case? Just very briefly. Local projection is just OLS of yt plus h on xt at each h, possibly with controls. It's easy to do. People actually used to do something more complicated. From Sims 1980, they modeled the full probability distribution and just had a full probability model called a vector autoregression, where they take the full data, OT, so all the data, and they regress it on its lag values for some number of lags, say p lags, with coefficients AP for each lag. This is so for each variable, this is a linear regression on the lag values of all other variables, and then with some error terms. And so we can collect these coefficients into matrices, and you can estimate this by OLS, GFM, MLE, Bayes, so on. If there's a contemporaneous relationship in addition to a p-th order Markov relationship with past values, we can write the structural equations as OJT depends on the other variables plus all of the past plus a structural error. And so if we assume linearity, we would write this again as a linear regression type equation, but then with the dependence of OT on the other variables in OT, and so there's a sort of contemporaneous coefficient B0. Moving this to the other side gets you an S bar where you have the lags and the present value, and then if we're acyclic, there exists an ordering such that B0 is lower triangular. So this is just, so from the causal ancestors to the causal descendants. And so then a lower triangular matrix is invertible, and we can get back, and this will relate, so the structural coefficients to the regression coefficients. And if the errors are mutually independent, we can get back this I minus B0 transform by taking the Cholesky decomposition of the variance of the errors. And so this will identify the magnitude of the shock up to scale. So the magnitude of all of these effects up to scale. And then you can do the IRF by simply iterating forward. So in the first period, it's the initial inverted shock, and then in the next periods, if you assume that this model is right, you can iterate forward. So that's what people used to do. This led to a focus on shocks rather than effects of shocks rather than effects of variables, the UTs rather than the ETs. And so there are a lot of proposals other than Cholesky ordering that people did, some of which were derivable from well-specified structural systems and some of which weren't. And so a lot of this kind of ad hoc identifying assumptions were used based on parametric models with no sort of clear relationship to structural models, led a lot of people for many years to sort of not trust bar results very much at all. So it's fully equivalent to local projection. If you just include in the local projection, so your linear regression of OJT, all the causal ancestors of OJT contemporaneously, plus all the lags. And so the difference is that you get coefficients on the actual variables rather than the shocks, but those are identical if you multiply the value by just the residual standard error of the local projection so that it's in units of the actual variable. This is basically just S-bar with Cholesky ordering is just backdoor adjustment with linear homogeneous mean model. And so, you know, if you think that's good, then maybe this is okay. If you think that's bad, then maybe it's not okay. The IRFs will differ between these different approaches in finite samples because you do some extrapolation, but they're like the distribution is equivalent. And if you sort of include an arbitrary number of lags, you get equivalent results. And so LP versus VAR is not sort of OLS versus something weird, it's OLS versus OLS. So you should base that on statistical properties, which some people have done some analysis of this, and the answer is it depends. Very briefly, other things that you can do IV in time series. You include an external instrument, WT. XT is the treatment, Y is the outcome. Impose the standard IV conditions, exogeneity, exclusion restriction, relevance, monotonicity. You can get a late. You can even estimate it by, so replace OLS with IV. You get local projection IV. And you know, it turns out that that's actually equivalent to just including W as the causally first variable in the Cholesky ordering, at least in the sort of asymptotic sense. And so IV is something that you can do if you sort of have a shock that's determined by IV. There's lots of other things that people do based on like long run restrictions, sign restrictions, sort of mostly defined in terms of parametric models. It's not really clear what's going on with those in terms of causal effects. I think that's sort of an interesting question to answer, what those actually mean. But answer is I don't know. Finally, what if we want to know the response to a full sequence? I realize actually, no, I have 2 minutes, so that's about what I want. So point exposures describe responses to temporary interventions. So leaving xt plus h either unmodified or at value determined by response to treatment. Maybe that's not what we want to measure. Maybe we want, so, you know, if we want to say, do we think that expansionary monetary policy is effective? Then maybe we don't want to measure the effect of expansionary monetary policy that under the current policy regime will get reversed immediately, but we want to actually measure the effect of, say, ongoing expansionary monetary policy. In the linear causal model case, intervention effects are additive, and so you can just get these compound interventions by putting together the sequence of IRFs. The sequence-based perspective has been used for all sorts of interesting results in estimation, identification, and computation in linear macro models. It sort of says that, oh, if everything is linear, you don't have to worry about these effects that, you know, may or may not be what you want for estimation. In the general nonlinear case, the sequence of treatments is called a treatment strategy. You can show, so there's a section in the Ernon and Robbins textbook on this, that under sequential exchangeability, so if you have conditional random assignment given the past and potentially controls in each period, and you have an appropriate overlap condition, then there exist estimators which can identify this, but note that the possibility that treatment affects future control variables means that you can't simply condition on the full path of treatments and the full path of controls, because once you've conditioned on the treatment, you change the value of controls. And so there's sort of relatively complicated ways of accounting for this. Arguably the simplest is, so inverse propensity is sort of always applicable. You sort of reweight to the distribution given by the conditional assignment, and there you multiply by the inverse of the product of propensity scores. So this is sometimes called, so your estimates of means and other outcomes are sometimes called marginal structural models, and that's the thing you want to look for. If you're going to use conditional mean estimates, you have to do nested conditioning. So the conditional expectation of the conditional expectation of that, and that gets a little complicated. But if you want a doubly robust estimate, then that's sort of the way to do this. If you want to measure the effect of a policy, so conditional changes, so allowing the future x's to depend not just sort of in a deterministic sequence, but in a value that depends on realized values of other observations, you can also measure the effects of a policy there using similar sorts of estimators. This has sort of been applied in panel data in many settings. In economics, mostly people try and answer these questions with fully specified dynamic models, which sort of, you know, if you have a correctly specified causal model, that can certainly work, though this is usually done in sort of a highly parametric fashion. So in conclusion, time series induces statistical and causal dependence across observations at the same and different times. You can perform estimation and inference under stationarity and weak dependence. So if you do appropriate transformations, if you are lucky enough that the sort of historical patterns don't have too strong of an impact on present patterns, then you can do things that look very similar to what we're used to, so simple averages. And there are sequential analogs of random and conditionally random assignment that will allow us to measure sequences of causal effects called impulse response functions. Linear case can be done with local projection or VAR, or you can apply things that look more like inverse weighting, or augmented inverse weighting, if you're not going to assume linearity. So lots of references. So that's it for the lecture today. I don't have a topic chosen for the next lecture. There was unanimity on time series, and then every other topic got approximately 1 vote. So any suggestions on what you want to see on Thursday?
I'm interested in sort of estimating distribution.
Okay, yeah. So especially, so things on the syllabus I have, I can prepare in short notice. So distributional effects, quantile regression, distribution regression. We'll talk about that on Thursday. So I'm going to release, an actual description of the final project sometime later. Several of you have sent in to me just like a general description. So, what paper you're interested in replicating, or what is the basic idea of your research project. Be thinking about it this week. Come talk to me soon, and I'll probably, hopefully by next week, have released a formal description of what I want you to do for that. I won't, the syllabus says that there are 2 sort of within term replication assignments. I'm not going to do 2 of them. You've done 1, and you'll have a final project, and that will be the total for the class. Yeah.
Do we have a class Tuesday?
Next Tuesday? I checked the calendar, and I think yes.
Okay.
Yeah, so I realize that many people travel during that week. So this was what I was talking about with AIPW. I said, I haven't seen the paper. I don't think anything is stopping you from doing it. The only sort of thing that you would do is you would do the blocking for the cross-fitting approach. These papers do something like it with, so in what's known as the adaptive setting, which basically, like, certain components of the time series are IID, and then the sequential component comes from you are making decisions over time, and so it's your own decisions that induce the dependence. That's sort of not quite the same. You don't rely on the same asymptotics, but I don't think anything is stopping you from this, and it seems so straightforward that presumably, if it's not out there, somebody's working on it. But if you want to just run it, the formula, here's how you do cross-fitting. I think it'd be a good idea. There's some, so I will say that there are some complications having to do with, so these robustness conditions still apply. Semi-parametric efficiency theory, so if you want to get the semi-parametric efficient estimator in time series models, that gets a little more confusing because That will depend on your model of the dependence across the process. So there's sort of this regular estimator condition may depend on features of, so the time series properties of the model may depend on structural properties of the model. And so semi-parametric efficiency bounds in time series settings have been derived in a small number of cases. There's some papers by Ivana Kamenger that have looked at that, but there are still sort of open theoretical questions there. That said, double machine learning just requires this sort of orthogonality condition, which can be described in terms of the moment. And so it may not be optimally efficient, sort of what is the optimally efficient thing to do. But whether it gets you the better rates, I don't think that there's any barrier to applying time series versions of the proofs that would allow you, for example, to include machine learning estimates for these. But I haven't verified that, so maybe people haven't done it because it's hard. But then again, you know, inverse propensity weighting paper was, so they had an earlier version, 2011, but this came out 2018. Actually, the OLS local projection was also quite recent, like people realizing that you can just do OLS and that works fine, was also quite recent. And so this whole literature seems sort of delayed. And in part because there are many sort of technical issues with the asymptotics that are sort of very challenging that people focused on instead. But yeah, I think it's an exciting area.